Hey everyone, welcome to Ibis because SQL is everywhere and so is Python. I am Philip Cloud. I'm a software engineer at Voltron Data, and I work with my colleague Gil Forsyth and a bunch of other great people there. Gil isn't presenting here today, but he did a lot of this talk, so I thought it was only fair to call him out. These are the places you can find us on the internet. I'm CP Cloud on GitHub. I have a YouTube channel called Philip in the Cloud where I talk and sort of live stream usually every Monday about Ibis, and Gil is G Forsyth on GitHub and similarly on Fosstodon. So we're here to talk about Ibis, which is a library built by all these great people and a bunch more who aren't visible on this slide. But first, let's sort of set the stage and talk a little bit about what kind of problems we're working with here. This talk is sort of for people who have kind of done many, at least one of these things. And let's be honest, most of us have probably done at least one of these things. Translated code from pandas to PySpark, prototyped in pandas and thrown it over the wall to data engineering, been the data engineer on the other side of that wall, used Parquet as a cross-language serialization format. And none of these, there's no sort of judgment here on any of these tools. They're all useful in their own right. And often people are sort of working in Python. And what does that look like? So the PyData stack is this large stack of tools that kind of spans a lot of different use cases, all built on Python, of course, and NumPy and pandas. And it's all sort of, to quote Jake Vanderplas, unreasonably effective. And often users are presented with a PyData stack, and there are kind of two limitations here that are fundamental to the stack. And one is that data are local; they live sort of where you're doing the compute, and that data fits in memory. So how does that what does it look like when we need to kind of do kind of a typical big data workflow with this set of tools? So we've got our local machine. It's got pandas. That's the pandas logo, if anyone's unfamiliar. And then let's say we've got our remote engine Trino on the right. And so local, we're going to connect to our database. We're going to extract a table, ratings. We're going to pull all of the entire table that's on disk or in memory on the Trino cluster back to our local machine. Then we're going to do whatever we need to do, parse the types, and do whatever kind of analytics you might need to do. And like this pattern is a lot of what people do, and that's fine, but you're leaving a lot of stuff on the table. The remote engine is not just a data store, it's actually a full-blown SQL query engine that has a lot of functionality, scalability, and performance, and perhaps it's even very expensive to run this. And so you're kind of leaving a lot on the table. And this actually shows up a lot in respect to the PyData stack when you're interacting with the enterprise. And there isn't really kind of a great way to hit these other systems, but still sort of feel like you're working in the PyData stack. And so that presents us with kind of the translation problem. Nobody really wants to write things twice, but we have this split. We have the local, the dev side of things, which is like polars, pandas, DuckDB, SQLite, and then we've got distributed and production, which is DAS, Spark, Trino, BigQuery, Snowflake, StarRock. There's a bunch of this stuff. And these are not exhaustive, and some of the tools kind of bridge the gap or sort of blur the lines here. But one of the tools that kind of nominally promises to do that is SQL. Right? It's like, let's talk about SQL. It's been around for a long time. Everyone who's here has probably written a large amount of it or written multiple query engines to execute it. But the most important fact is maybe that it's everywhere, and it's usually between you and the data. And this is a tiny subset of the systems that all sort of, interact with SQL in some way. But of course, it's not without its problems. Some pros are that it's standardized, kind of, but not really. We'll get to that. It can be very concise. Some cons are that it's hard to test. It's like, do you want to write like asserts in SQL, or can you? And I don't know, maybe. It can be pretty challenging to learn and to deal with. And then slow feedback is another thing. Like you may actually submit, there may be seconds before you sort of figure out, that you made a typo in a column name or something like that. And so you might just be waiting a very long time to get to that typo, and that's the issue with slow feedback. So let's see if we can kind of bring some SQL to bear on the problem we had before. We've got our local execution. We've conjured a query somehow, and then again we go through the connect. We connect to the database. We send our SQL query over. We execute the query, and then we get back our results in some form. Now, let's go back here. This is not quite a tight loop. It can be hard to compose queries, like if your engine doesn't support common table expressions, or then you need to use subqueries and maybe you have to repeat those or break those out somehow, and maybe now it's in a string, and you're also running against your production database while doing exploratory data analysis. So this is just a lot of issues here. And to get that rapid feedback, you think, okay, well, maybe I'll get a local sample. I'll pull down a SQLite or a DuckDB, and like, yeah, okay, I'll kind of deal with the SQL differences. And so you iterate locally. You got your SQLite database. You're iterating. You finally get the query you want. You connect to the database, send that query, get back, execute the query on the remote, get back the results, and it's like, okay, we're done. Problem solved. Talk is over. It's like, not quite. There's a couple issues here, and the first one I want to talk about is the translation problem. It's the SQL standard is a standard, but sort of XKCD, insert XKCD meme here. How standard are these standards? It's like before with our local execution in SQLite and Trino, we now have to deal with a dialect translation, a SQL dialect translation problem. So let's look at a simple data cleaning task. I've got 3 columns. They're all strings coming in initially, but I want to convert 2 of them, the average rating column and num votes, to the things that they sort of look like here. And so that's floating point for average rating and integer for num vote. It's num votes. And we're just going to look at this from the perspective of 2 different databases. So on the top, we've got SQLite. In the bottom, we've got Postgres, and already things start to diverge, right? We've got apparently simple problem, but with SQLite, our double precision type is called real53, and in Postgres, it's double precision, and then integer in SQLite and big int in Postgres. And it's like, this isn't a huge amount, but like things tend to grow over time. And what if you have to parameterize your query? Do you have one big query, or do you have like 1,000 smaller queries? And it's like, well, maybe I want to like process those each in parallel, or I want to make a big union. There's all, or maybe the parameters themselves are like conditional. It's like, yeah, things kind of get out of control quickly. And then we also want to write stuff in Python. We like Python, and we want to use a Dataframe API or a Dataframe-like API to query our data. And I mean, initially, like we don't want to write SQL because, well, we want to write Python, and there's a bunch of complexities of SQL, I think, that aren't necessarily desirable to have from, if you sort of want a Dataframe API. So what's a solution presented with these problems? Translation problem, parameterization. We want to use Python, and we don't want to write a bunch of SQL strings in Python. And some people, including myself and pretty much everyone who's probably ever had to use SQL from a different language than a SQL terminal, presented with that problem, think, okay, I know, I'll just generate some strings, no problem. Let's come back to our simple example here. It starts off simple enough. Fine, you've got a get engine D type that, like, given a string and a dialect, knows how to turn that into Postgres in this case, and you could fill in SQLite and get that. Okay, totally fine. If that's all you had to do, cool. Like, you don't need Ibis. But now we're modifying, maybe we modified our query and we want to add some additional columns, and function names differ in SQLite and Postgres, and even like things that are kind of, maddening, like, the argument order of log may differ, for example. And then maybe your engine has optimized versions of certain functions that Ibis could, or sorry, that you could actually use, but you can't because now you have to add some more code to figure out what those functions are. And then finally, output formats vary wildly between different engines. Maybe you can get back something in Pyaro format, or like sort of native data frame, or maybe you're getting back a list of Python tuples from like SQL Alchemy. I mean, it's just, there's a lot of variety there. And again, with the parameterization, maybe you've got conditions on those things. Like if they're just constants, then yeah, it's not a big deal. But you have to encode that transformation logic too. And of course, outside factors, things you don't really have control over. People telling you, all I'm saying is, to be great if we could X, we'll fix it later. This is a high priority request from someone, and then things just kind of grow and grow and grow, and get kind of out of hand. So this is totally fine. Stop here if like this is all you have to do. And then it's like, okay, cool, we added a left join on another table called basics on the tconst column. Nothing else changed. That's also fine. And then it's like, okay, well, now we want to change the name of the join column from the ratings table. And then the ratings table itself may also have a different name. So we need to look that up in a join key. Like it's like, okay, maybe this is fine. And then from here, it just starts kind of spiraling. You've got char index that's itself is a templated format string going into another format string. And it's like, okay, well, fine-ish char index. And then it's like, okay, like what sort of Cthulhu hell are we in, where like we've got like multiple levels of conditional templated strings. And like, if I were giving this talk to a live audience, I would now ask, who here can say with full confidence that something like this wouldn't happen at their workplace? And like, anyway, so that's sort of the thought behind this, is like, yeah, this may seem like a caricature, but like I've definitely worked in places where this kind of code existed. So presented with this, you might just be like, SQL is really difficult at first, but once you use it regularly and learn more about it, it's worse. And there's sort of an interaction effect here with Python. So like, it's not fully SQL's fault here. And so you're just like, no, thanks, I'm not going to use SQL. But remember, it's everywhere. And we should appreciate the fact that there have been decades of humans and human years working on making query engines really fast and performant and memory efficient and scalable. And like, if you just throw out SQL and say, oh, I'm going to go back to pandas or whatever, you're leaving a ton of stuff on the table. So where does that leave us? SQL standards are sort of standard. SQL can be a little bit convoluted. It's definitely difficult to use it from client-side languages. String generation leads to madness, but we still want to write our code, our analytics code in Python, and we want to take advantage of all the human knowledge and effort that's been poured into modern query engines. We shouldn't just leave that kind of on the table. So what if, instead of generating strings by hand and dropping into Cthulhu hell, use a type-safe Dataframe API that eventually generates strings? And that's Ibis. It's a lightweight Python library for data wrangling. It's a Dataframe API. I think we've got 17 query engines now that we support. And it's a deferred execution model. And for anyone who's used R in the past or familiar with R, it's kind of similar to dplyr or dbplyr. So let's take a look at how that kind of plays out. You're on the local machine, you've got Ibis installed, your query engine is Trino. You connect, not so different. You get the table out. The main difference here is that you're just going to get the metadata from the database, and then Ibis is going to be like, cool, now I know the column names and types. Ibis has its own type system that it's going to use to validate your expressions, and then it compiles those to SQL. You set that SQL query gets sent to the engine, and then the engine executes it, of course, and then you get back your query result, and you can get back query results in different formats. One benefit of separating this is that if you have a separate metadata store, Ibis can extract that, can get that information from the metadata store without actually having to hit the query engine itself. So that's kind of nice. And you can kind of go, kind of as deep as you want. Like if you know the column names and types, you can build a totally engine abstract, like data frame expression. And that can be useful for developers who are using Ibis as a library if you want to sort of provide that interface to your user. And how do we do this? Well, we do this with like strong typing and a fairly sophisticated type system and validation as you construct expressions. So this is kind of an example bit of code. You've got a ratings table. You've got a column called numVotes, which is a string. You try to compare that to a number, and Ibis says, hey, you can't do that. Strings and integers are not comparable. You can cast that. Ibis knows that casting a string to an int is a valid operation, and now the data type is int, and so it lets you do that comparison, and it constructs basically a select statement. All right, demo time. Okay, I'm going to stop sharing my screen for a second. Switch here. Sharing. Okay. Let's see if we can get this going. Screen share. Share this window here. Share. Okay, let me just bring it back on my screen. All right, hopefully everybody can see that. I'm gonna import Ibis. I'm using IPython right now, and I'm gonna go a bit quick. I'm not gonna type everything out by hand just because we're limited on time here. So I've got a Trino instance running locally, and it's using the Postgres SQL connector, and I've got some tables in there. And there's kind of a bunch of stuff in here, but what we're interested in is ratings and basics, because we're going to do a simple analysis of looking at the top 10 movies from public IMDb data. And so we're going to pull out this ratings table, con.table ratings, and then we're going to pull out this basics. So sorry, let's first look at ratings. Ratings is kind of this example we've been showing all along. We've got a movie, we've got its average rating and the number of votes that went into that average rating. tconst is an identifier that uniquely identifies the movie. Then I'm going to pull this basics table, con.table basics, and that is going to give like a bunch of information about the table. Sorry, the movie. So it's got the tconst identifier again, what kind of movie it is, primary title, and a bunch of other interesting things. We're going to filter some stuff out. We only really care about movies. We don't care about TV episodes or TV movies. We're just looking at sort of box office style movies. And we're going to filter out the adult films because we're going to keep it kid friendly here. So that gives us this table. We've only got movies now. And then I'm going to select columns out, basics.select, tconst primary title. That's all I really care about for basics. And then for ratings, I just want to sort of cast those columns to the right numbers. That's sort of our data cleaning task from before. And now the representation in the table has changed a bit. We've got tconst, again, we've got the numbers there. And then we're going to do a join. We're going to say join equals basics dot join ratings tconst. And notice that all this stuff is executing immediately, and that's because Ibis itself is doing all the expression and type validation. It's not sending a SQL query. It's not compiling a SQL query for every expression you write, sending to the database, checking whether that's correct, and then getting metadata back. It's actually just sort of doing it all itself in pure Python. And then what we're going to do is we're going to say, we're going to use this shorthand method for Ibis called topk, which is basics rating. Sorry, let me show basics ratings real quick. Top 10 of that, or the first 10 rows. That's going to basically execute enough of the joins that you can get the top 10. Sorry, not the top 10, the first 10 rows of that, which is an arbitrary set of 10. And to get our top 10 query, we're going to say basics ratings, primary title, top K, 10 by basics ratings, average rating, and we're going to take the average of that average. Rating, mean. And it's like, okay, cool. We're executing our query, and we've got a bunch of stuff that is not, it's stuff I've never heard of. Maybe it's really popular elsewhere, but it's a little suspicious that they all have an exact average rating of 10, right? And so if we take one of these basics ratings and we look at the primary title, we say primary title, look at Chasing Tokyo. We look at the num votes of that. It's like 5 people have voted on this movie. Okay, so it's probably a bit over indexed. So let's filter basics ratings to have only movies that have at least 100,000 votes. And then we'll reconstruct our top movies expression. Whoops, top movies equals that. And now we'll see. We've got some movies that are probably a little bit more familiar: Inception, Pulp Fiction, Schindler's List, The Godfather, to The Shawshank Redemption, etc. And there's some ties here. You can see 8.8, 9.0 is like a bunch of films, and so you might get a different set of results the next time you execute this query, because it's not a totally deterministic order by. Now, top K just sort of desugars to a group by. And then one really sort of nice thing about this whole shindig is that I can just fire up the Postgres connector, which is the same thing the Trino database is hitting, and I can literally take my query that I just ran against Postgres. Boom, done. Got the same results, modulo the sort of non-determinism from the order by. And I didn't have to change anything about my code. It runs on Trino, it runs on Postgres, and that's sort of the power of Ibis. And there's a couple other nice things, like what if I want to see the SQL of this? And it's like, sweet, now I can see the SQL that Ibis has generated and sent to the query engine. You can even change the dialect if you wanted to look at it in terms of Hive. Okay, unknown dialect Hive. Let's try Impala. All right, cool. We got that. So we've changed our quoting behavior and perhaps some function names. That's pretty nice. And then you can also, of course, convert stuff to PyArrow if you want, not just data frames. Boom, PyArrow table. Okay, let's go back to the slides. That is the end of the demo. Okay. So what do we see? We saw select, filter, aggregate, join, combining expressions. There's a ton of other stuff going on. I encourage you to look at our docs, ibis-project.org. These are the backends that we support. There might even be more that we support. I know people are using with Redshift. I think we get issues about that occasionally, which I think they're just going through the Postgres connector. So that's kind of interesting. I think people have tried to use it using it with Azure SQL. And there's some new stuff coming down the pipe as well. Of course, it's not a silver bullet. There are no golden tickets, and every other sort of ism around no free lunch. Floating point math exists. There's a bunch of stuff that like you can't do. That's not a bunch of stuff. There's a few things that are very specific to how a backend works. Regexes, data dependent function behavior like DuckDB, for example, will trim white space from the ends of strings when you cast like a string to a number. So what's next for Ibis? We've got a cross-dialect.sql method, which is a method that allows you to put in DuckDB SQL and run it against Trino or Snowflake and run it against DuckDB or any sort of mishmash of mix that you kind of would want to mix up, would want to sort of, run against your database. We're unifying our UDF API so that you can define your UDFs independent of a particular database. More DDL support, more logical and simplified kind of internal logical optimizations, new backends. I think our Oracle backend is landing in 6.0. There may be a DB2 backend on the horizon. Who knows? And then please get involved. Like we're around the internet in many places. So happy to get involved. Okay, it looks like there's a ton of questions. So I'm going to go to the next slide, which I think is the last slide. Yes, it is. These are the places you can find us and the project. And these are some of the ways. There's probably more ways to install Ibis. Okay. Okay. Let me scroll.
Philip, so good.
Thank you.
It's very interesting to see the different use cases, where, and perspective in terms of, hacking SQL versus writing in Python. One of the questions that came up is, in terms of functions, when you use like engine functions versus Python functions, can you use both? Can you mix and match where they run, that kind of complexity questions?
Yeah. So if a functionality is like available in the database, then like we try to push as much stuff into the database as possible. So for example, we recently added support for array map and array filter, like the functions that sort of allow you to apply like a lambda function essentially to a list of elements per row. And that's all done in SQL. Like we take your Python lambda and we like turn that into some SQL. It's restricted in the sense that it needs to be kind of it needs the ability to be turned into SQL, but that basically just allows you to write the same kind of Ibis expressions against that array as you would if you had to sort of unnest it or whatever. And regarding like sort of pure or I guess like non-SQL Python functions, that's part of the library that we're actively working on now. We're adding UDF support to the backends that kind of allow us to do that. So DuckDB is one that recently added in their 0.8.0 release. SQLite has this, Postgres has this. We've actually added it for Snowflake as well. So yeah, I hope that answered the question.
Yeah, no, that's cool. People also asked about that UDF API. I guess you're working on it, and in general also about documentation and how to see those examples. One thing that we talked prior to the event was that you might come up to the Trino community broadcast, and we'll do more demos and stuff there. And also, I guess there's a lot of documentation available on the Ibis project website, and then beyond that, people just have to tell us, right, what they need. I guess
that's true. Yeah, I mean, open an issue, like we're pretty responsive. I think it's one of the things that like kind of helps the project like do well, which is just having people, even if it's a complaint, we're happy to discuss it. It looks like somebody's asking if this is similar to Link SQL and Python. It's Link is definitely a thing that like at least some of us on the team have like interacted with before. So it is like spiritually similar to Link.